Hi there. In this video, we'll look at problem 24 from the semester exam review packet. In this problem, we're told that a particular function f is continuous and differentiable on this interval, and we know that it contains this particular point as well as this particular point. All right, and we're given a whole list of statements, and we're supposed to figure out if those statements are always true, sometimes true, or never true. So let's take a look. Part A asks, does f have to be an even function? Well, even functions, okay, that term comes from the behavior of even powers. Even powers all being symmetric with respect to the y-axis, okay? Just like 5 squared would give 25, and also negative 5 squared would also give 25. So it's symmetrical like that. But this graph is not symmetrical in that way. In other words, f of 5 is down here, and f of negative 5 is down here, whereas f of 5 is up here. All right, so it might possibly be an odd function, but it's definitely not even. All right, so we can say definitively, regardless of what else this graph does, as long as it hits these 2 points, who knows what's in between, it cannot possibly be even. So the first one is never true. Okay, statement B says, does f map 0 to 0? Well, it might. Okay, we can draw an example where it does hit the origin, but we can draw an example where it doesn't. So the correct answer here is sometimes. Maybe the graph hits the origin, but maybe it doesn't. Part C. Do we know for sure that f prime of C is 0 for some C value between negative 10 and 10? Let's remember this means the graph has a horizontal tangent. And one thing that should strike you as odd is that they've presented as inputs the values which are actually outputs. Okay, so they're sort of messing with your head a little bit to see if you're paying attention. But in any case, is that necessarily true? Well, maybe, maybe not. All right, there might be a C value where the graph has a horizontal tangent, or there might not. So this is going to be a sometimes situation. By the way, again, just to point out how this is weird, we don't even know if the function is defined beyond this interval. So we really shouldn't even be talking about values in the domain that are outside that particular interval. So it's just a little bit strange, but they're just sort of seeing if you're on your toes with that. Okay, part D, do we necessarily know that the derivative is positive everywhere between these 2 points? In other words, is the function always increasing? Does it always have a positive slope? Well, it might, as this example shows, but then again, it might not. There might be some parts where the function decreases. So this statement is only sometimes true. Part E. Do we know for sure that the outputs are bounded in between the 2 outputs that were given? Or can it go outside those values? Well, let's take a look. All right, in graph A, I drew it in such a way that it stays below the top value and above the bottom value. So that statement could be true. On the other hand, I can make it go lower than that or higher than that. So graph B shows it might not, the outputs might not stay within this interval. So the statement is only sometimes true. Statement F. Do we know for sure that the slope is 0 for some C value? This time they're getting the inputs right between those 2 values. Well, as we said earlier, that might be true. Maybe there's a horizontal tangent somewhere along the way, or maybe there's not. So the statement is true sometimes. G. The slope is equal to 2 for at least one input between these 2 given inputs. Now there's an interesting statement. Where is 2 coming from? Let's see if we can do math and figure out what's going on. Well, between negative 10 and 10, we have a difference of 20. And from negative 5 to 5, we have a difference of 10. In other words, the rate of change, 20 divided by 10, is 2. And since we know some information about the function, namely it's continuous and differentiable, we know that the mean value theorem applies. And so regardless of what this graph looks like, let me clean up my picture. Regardless of what the graph may look like, we know that there's got to be some value somewhere where the rate of change is exactly equal to 2. Okay, so this statement, I believe for the first time, this one is the first one that's always true, and we use the mean value theorem to be sure of that. Statement H. The output is 9 for at least one input between these two values. Interesting. So where's 9? 9 is here. Okay, do I have to reach an output of 9? Well, I can go up and down. Lots of things could happen here. But does it make sense to you that you have to hit 9? If you're going to travel, let's think of this as a problem about sea level. This guy is 10 feet below sea level, and later on, he's 10 feet above sea level. Does it make sense to you intuitively that at some point he was 9 feet above sea level? He had to be. And the reason we know he had to be is because the graph was continuous. If it weren't continuous, then we could skip 9. Maybe there's like a hole there. But as long as it's continuous, you can be sure that it hits 9. That's called the intermediate value property, and it applies to all continuous functions. Okay, and I believe that wraps up problem 24. Hope you found this video helpful.